Hello and welcome back again to another advent of code in Ruby. We're on day 10, 10 days in a row of streaming. This is unheard of for me. So, Advent of Code, if you're not familiar, is a 25-day coding challenge that happens every year, December 1st through December 25th, and it just like a nice little advent calendar. You pop open and instead of getting chocolate that gives you diabetes and then you die, you get coding, which makes your brain smart and you become mighty. Although, to be fair, most of the problems so far have been pretty trivial. We haven't gotten to hard stuff yet, so we'll see how that goes. Anyway, we're back at it, so let's get right into it. Let's read through this. So far, the lore is that we are terrible human beings who are hacking every system that comes our way as we try to get on an airplane and go on vacation. Okay, so last time what we did, staying in our aircraft, we hacked the data port by way of paper clips and used an algorithm to hack their algorithm. So that's not great. That's not great. That's our bad. But it's fine because, you know, it's Christmas and we're trying to get away from everything. And 2020, that's what it's all about, right? So let's get into this. Day 10. Adapter Array. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared, you make a list of all the joltage. Jolt? Is that like a real? I don't think it's a real unit of anything, right? I don't know anything about electricity, but that doesn't sound real. That sounds fake. That sounds phony. You make a list of all the joltage adapters in your bag. Each of your joltage adapters is rated for a specific output joltage, your puzzle input. Any given adapter can take an input of 1, 2, or 3 jolts lower than its rating and still produce the rated output joltage. Okay. Okay. In addition, your device has a built-in joltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. If your adapter lists were 3, 9, and 6, your device's built-in adapter would be rated for 12 jolts because 9 plus 3 is 12. So we just like always... That's a weird way of like being like, hey, by the way, I know that my best adapter, I'm rated for like 3 more than that. That's very weird. Treat the charging outlet near your seat as having an effective voltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to have to resort... I can read, really, I'm a literate human being. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to get to your resort, and realize you can't even charge your device. If you use every adapter in your bag at once, what is the distribution of voltage differences between the charging outlet, the adapters, and your device? Okay, I'm not sure if I really understand what this problem is asking for yet, but that's okay, because they're going to give us an example, and it's going to become really easy. For example, suppose that in your bag, you have adapters with the following voltage ratings. Okay, and they give us a series of numbers. With these adapters, your device's built-in joltage adapter would be rated for 22 jolts, because the highest number is 19. That makes sense, yes. Because adapters can only connect to a source 1 to 3 jolts lower than its rating, in order to use every adapter, you need to choose them like this. The charging outlet has an effective rating of 0 jolts, so the only adapters that could connect to it directly would need to have a joltage rating of 1, 2, and 3. Okay, this kind of makes sense. So we kind of need to order these in a way that we can string them together. But isn't this like basically just sorting? Like, is this not just like a basic sort here? That's what it sounds like, right? I feel like I'm missing something here. Let's go on. The charging outlet has an effective rating of 0, so the only adapters that could connect to it directly would need to have a joltage rating of 1, 2, or 3 jolts. Of these, only one you have is an adapter rated 1 jolt. difference of 1. Okay, so our 1 is done. From our 1 rated adapter, the only choice is your 4 jolt rated adapter, difference of 3. Okay, so next we have the choice between 5 and 6, right after that? Similarly, the next choices would need to be rated... Why would it have to be rated 6? Wouldn't the 5 be Wouldn't 5 be okay? Oh, I skipped a step. From the 4 rated jolt rated adapter, the adapters rated 5, 6, 7 are all valid choices. However, in order to not skip any adapters, you have to pick the adapter rated 5. Similarly, the next choices would need to be rated 6 and then 7, with a difference of 1. The only adapter that works with the 7 rated adapter is one with 10. Let me actually just like sort these, because I feel like this is just like a basic sorting thing, right? So let's just put it like this. This seems like a very convoluted way to say that if this input works at all, you can just sort the numbers, and if it doesn't work at all, then sorting isn't going to help, but there's like no other way to get there. That's what it sounds like to me. This just seems like a really, really weird way of saying, hey, we need you to sort a list of numbers, which is a very trivial thing, so I'm hoping I'm missing something here. How does that 16 get up to 19? Oh wait, no, that's only a 3 gap, so that's fine. So let's follow along these instructions, right? Similarly, the only adapter that works with the 7 is the 10, that makes sense. In the 10, the choices are 11 or 12. Choose 11, difference of 1, and then 12, difference of 1. After 12, the only valid adapter has a rating of 15. That makes sense. Then 16, difference of 1. Then 9, difference of 3. Finally, your device's built-in adapter is always 3 higher than the highest adapter, so you're at 22. For this example, when using every adapter, there are 7 differences of 1 jolt and 5 differences of 3 jolts. Okay, so do we need to care about that? Here's a larger example. In this example, we're just going to sort these algorithmically here because screw that, I'm not doing that. Where's my... Here we go, this is what we're looking for in life. IRB. Did this not, like, copy everything in? I don't... Okay, it did. I don't know why this is playing weird. Also, I want this taskbar to go away. Go away. Thank you. Oh, this is a mistake. This is all a mistake. Do this. We copy pasta. We end. Still want this to go away. Thank you. We're going to cast these all to integers, and then we sort. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 10, 11. Okay, then we skip. Okay, so we are counting the differences here. Find a chain that uses all of your adapters to connect the charging outlet to your device built-in adapter and count the voltage differences between the charging outlet, the adapters, and your device. Was the number of 1 jolt differences multiplied by the number of 3 jolt differences. Okay, so this is how we turn it into an algorithm. That all is fine. It's not lining up the way I want it to. That's very, very annoying. I want this to just kind of like resize together. There we go. That's much nicer. Okay, so let's get back into our console. We are on day 10 now. Good grief, Charlie Brown. Day 10, let's go. We are going to copy problem 1 from yesterday. Perfect. And we're going to create a new input file as well. We can test our code out. We have a lot of open directories now, so let's just close these all up. Don't need any of these. Okay. Close all these windows too. We don't need any of these tabs. Okay, so first off, let's copy our big sample input. Big sample input energy right here. Let's take a look at our actual puzzle input and see if there's a leading new line. There is not, so we don't need that for consistency. Let's look at our problem 1. I don't think we're going to need to borrow anything from find weakness or sums from last time, but we, as always, are going to be holding on to our input lines. And we'll actually start this the same. We're going to turn our input lines into... Actually, let me just throw this into the directory while we're at it, while I have this open. Want to move that there. Okay, cool. So we have that for later. That's fine. Let's change this right now to input sample. Ooh, okay. So I think the first thing we do is we just sort these. Call this jolts because that's what we're dealing with here, and we can sort right here. So we need to see we need to find the difference between each previous, we're going to iterate through the entirety of input lines, or rather jolts. We're going to iterate through each of the jolts and basically be like, hey, what's the difference between you and the guy before you? So to do that, let's take a memo of jolts 0, the first jolt, and then we're just going to iterate over a slice starting from the second element, which is numbered 1, and go all the way to the end. That. Okay, so this is just going to give us every jolt as we go through, and let's keep a memo hash so we can just remember the offsets. These are the offsets we've seen so far. And at the end, we're just going to preprint the offsets so we can make sure that what we're doing is in the right ballpark. So these are sorted, so we know these are going to be increasing. So instead of calling that, let's call it previous. The current jolt, I feel like there's some sort of a pun about electricity there, right? So offsets, offset, If that doesn't exist, let's start off at 0. And then we increment it by 1. Rather than store this as a variable, we could do this as a tap, but I think this actually reads a little nicer this way. Like the other way we could write this is to this expression tap we could do this instead, but I think this is actually a lot. I think this is worse to read. I don't like this at all. Let's keep with our original version. Sometimes I overuse tap, so maybe that's something I should be more aware of. Tap is just a way that you can pass a block. You can basically pass any variable a block, and the block will yield that variable, and you can have little side effects happen, but it will return like the original variable. So you kind of create like a little scope there. Okay, so we also need to make sure previous equals current, so that we're iterating this as we go along. Okay, let's see what this returns. We have no compilers this time. We do not. That's good. That's good. That's nice. We are in this larger example. In a chain that uses all of the adapters, there are 22 differences of 1 and 10 differences. So we're off by 1. That's really weird. Why are we off by 1? That's actually really confusing to me. Why are we off by 1 on both of those? I'm gonna think about this for a minute. Let me just, as a sanity, let's just make sure that somehow I didn't skip 1. Because that would be really bad, right? Let's also pretty print results size. $31. That lines up with the number of lines we have. I think it's really weird is like if it was off by, if only one of these was off by 1, I kind of understand that more. The fact they're both off by 1 is really weird to me. printing out a little bit more to make sure that I'm not like getting weird here. Okay, so actually let me clear first and then do that, and so it's easier to see where we started. Okay, so 1, 2, 3, 4, 7. Oh, you know what I'm forgetting? The outlet is 0. Okay, so this makes a whole lot more sense now. The outlet's always 0. And the yeah, the outlet's always 0, and I forgot about the jump to my actual device, which is always 3 more. That makes a whole lot of sense. So actually, previous always starts off as 0. And we don't actually need to slice here. Okay, we don't need that anymore. We don't need that. Yeah, that makes perfect sense. That was just a small brain thing we had there. I wish I could just make the start menu never show up on this monitor for me. I'm not sure how to do that, though. I should figure that out, though. I'm still printing out way too much. Let's get rid of that. And that's actually too much, too. Let's get rid of that as well. 22 and 10. And what we want is the number of 1 jolt differences multiplied by the number of 3 jolt differences. Okay. It'll be easier to copy and paste if we don't have that new line thing going on there. If we don't have like the solution equal. 220. Oh, they actually didn't give us a solution for the sample, but I mean that is correct, right? 22 times 10 is obviously 220. I think now we just switch over to our main example, our main input, and we just run with it, right? Okay. 69, nice, and 33, also nice. So now we're poised with an answer here that we have high confidence will be right, and we just need to plug it in and not live in fear, because the fear that exists in our hearts is that we will be stuck in a terrible timeout for up to a minute and not know what to do during that time and not know how to proceed with our life, living with that shame. We can't live with the shame. We just need to hope for the best and move on. We get a gold star. We moved on, and we were victorious. And I'm sorry, maybe I'm getting jaded by the how many gold stars I'm swimming in at this point, but I just feel really good about what we're doing here to ruin this air flight for all these people. Okay, whoa, there's a lot more stuff now. Let's see. Let's get into part 2. This is a lot of stuff. I was warned by a friend that part 2, you need to read it carefully because it's easy to miss something. So that's fine. Let's see what we got here. To completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. Every arrangement needs to connect the charging outlet to your device. Previous rules about when adapters can successfully connect still apply. The first example above, the one that starts with 16, 10, 15, supports the following arrangements. Okay, so there's some that we could skip. That's totally fair. The charging outlet and your device's built-in adapters are shown in parentheses. Totally makes sense. Given the adapters from the first example, the total number of arrangements that connect the charging outlet to your device is 8. Okay, so that's the number of lines there. That makes sense. The second example above, the one that starts with 28, 33, 18, I think that's our sample input. Yeah. Has many arrangements. Here are a few. Okay, that all makes sense. Total, this set of adapters can connect to the charging outlet of your device in 19,208 distinct arrangements. You glance back down at your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways to arrange them. Surely, there must be an efficient way to count the arrangements. What is the total number of distinct ways you can arrange your adapters to connect the charging outlet to your device? Okay. Okay, this is a bit... The first problem was kind of like a no-brainer. It was super trivial. This one, I think we're gonna just kind of like brute force maybe. But let's think about this a little bit. Let's start off. We'll copy over into problem 2 and start working there, so we don't clobber our first solution. And we'll switch over back to sample, so we can see how we did, how we're doing with the sample. I'm just sitting here, I'm thinking for a minute. I don't know how much of our old solution we're going to be able to use in our second part of our solution. Now that we don't need to use all of them, this almost sounds like kind of like a recursive search where we try to figure out like we try to figure out yeah. We try to figure out all the branching paths that we can take. This is interesting. This is interesting. Let's play around with this, and I think that there's an interesting solution here. I don't know if it's the best solution. I think first thing we do, we don't care about sort anymore. Sort is trash. Fuck sort. And what we're going to do is... Still going to start with 0. But we are going to add on to our jolts. Okay. So we have our jolt set up here. So we need to count the number of things. We don't need to count like the number of ways that it does each thing. So let's go back to our first instructions here and double check our rules. So any adapter can take an input of 1, 2, or 3 jolts lower. So every time we're increasing by 1, 2, or 3. So let's think about like a little recursive function here that we could. Let's see if I can remember how to do recursion this time. I wasn't last time. Input jolt. Arrangements from jolt. I think that reads a little bit more like English. Ooh, okay. So let's say that we're starting with an arbitrary jolt. If could include so we want to, for each jolt, we want to see if there's something here for each increment that we're allowed. Input jolt. Okay, so let's actually think about this in terms of start and destination. Offset. So we're going to try this. I think this is going to get like a little repetitive, and that's why I'm putting this into a loop here. If input include start plus offset. So we're going to test if it Ooh, I really like this. Okay, so we're gonna sum these. Can you actually do that? No, we want to do map and then sum. I'm thinking I'm not talking through every thought right now, and that's probably bad. Okay, so what we're gonna do first, we're saying, okay, is there a path forward? There a path forward? Input. If so, is there a path forward from this input? And that means like it exists in our little guy we got here. Oh, this is even better if we don't. Start, we'll call this start, and we'll call destination equals jolts max plus 3. It's better if we don't add it onto here because I think that makes the code a little simpler. I'm already liking this. Okay, so let me actually finish my thought here. If the input includes this new start, which could be like +1, +2, or +3, then that means we have more to go. Because our destination's never going to be inside this this thing, because our destination is always 3+. Does that make sense? I think that makes sense. So what we need to do is, do they call this arrangements, or what do they call this? Okay, they call them arrangements. Let's say call this arrangement count from. Ooh, I like this already. I like this already. So if it's inside here, what we want to do is arrangement count from new start destination input input. Take that down. Okay, now we have plenty of space here. Else, if input, if we're at the end, if we start equals destination, instead what we do is we return 1 from this map. Otherwise, if we're not at the destination and the next node is not, we can't get to the next node from here, then we just return 0. Oh, I love this so much. This is so clean. So what this is going to do is it's going to let's talk through how this would work on the sample input. Okay. So we start at 0. We start at 0, and we'll actually follow this along with Notepad. Okay. We start at 0, and first we test 0 plus 1. And we find that 1 is there, and we're happy. We're so happy about this. So now we have a collection that starts with 1. And we look inside there. And we look at 1 plus 1. 2, right? There's no 2 in here. So this is always going to return 0. And then we do 1 plus 2, because we go through the loop. We go through the second offset. And is there a 3 in here? No. So that's always going to return 0. And then 1 plus 3, that's 4. So we do get a hit there, so we return 1 there. Actually, this is a little cleaner here if I do this. So this all returns, and we find out. So these don't branch any further. So, sorry. 1 plus 3 is a valid route. So now we search for 4. And we do this for 4 plus 1. 4 plus 2. 4 plus 3. So every time we hit a good path, and eventually, things happen, and we end up at like maybe like 16. Or rather, let's say 19. And we do 19 plus 1, 19 plus 2, 19 plus 3. At this point, we've hit the end. So we return 1 back here. And if there were other paths, they would return 1 as well. And they kind of all sum up. And that gives us the number of paths that would have been valid if we start off with 1. That's really cool. Okay. And we end up with a... So I think this is going to work. I don't know if I explained that well. I probably explained this very poorly. But that's fine, right? Right? It's okay if we explain things poorly now and again. Problem 2. Oh, we did something wrong. Oh, we have a previous here from somewhere. Oh, no, we never changed our original thing. We never changed our main. Okay, so let's remove all of these. We don't care about any of this. Arrangement count from start, destination, input, jolts. Okay, cool. Do this. We didn't print out anything. We did not print out anything. So we want this to match 19208. Oh, and we got it. We got it first try. This is amazing. This is so cool. Okay. Let's we take off sample. And let's see. This is gonna turn for a little bit because this is. We could probably cache some things here to make it more efficient, but oh god, do I actually want to do this? Is this actually like too non-performant for us to be okay with? Oh god. This is taking so long. This is pause champ. Okay, new plan. I'm tired of waiting for this. So we're gonna do a little caching here. Arrangement count from cached. So if we have like the number 0, if we ever call this from like, let's say we call this from like the number 32. 32 is always going to result in the same exact thing, right? 32 is always going to add up to the same thing. Now we may hit 32 many times, so we can easily make this more efficient by caching. By caching based off of the start value. Actually, maybe it's nicer to just do this in line. Like, I could just have this call the cached form, but I think this actually might be fine. Cache equals. It's going to be called like a billion times, so we want to or equals bring that thing there. Bring the hash table initially. Cache start or equals. And we're going to switch back to our sample and make sure that we don't have any regressions by making. Oh, I missed that in the line. Okay. So the way this works is when we do, for example, a cache of 42, it'll see if we already have a cache element for 42. And if we do, we're just going to return that. Otherwise, we're going to run through all of this. So it means that if running start from 42 will only ever happen once. Okay. We want to change this to sample again. And this should be the same number we had before, but it should be much faster. 19208. Okay, so we're still good here. Let's see how much faster this makes everything. Wow, that was like... Is that like tail recursion, a tail recursion optimization? I think it might be. Some languages give you that sort of optimization for free, I think, actually. But I think in those cases, you need to be in a language where you can mark functions as being pure or not. Whew. So that's a big number. If we're wrong, it's going to be so hard to actually debug this and figure out why we did this wrong. So let's just hope that this works. Let's take a deep breath, paste this in, and go for broke. Let's do this. Let's do this. We're gonna be so sad if this is not correct. Then we're gonna be in the timeout of shame of 1 minute. But I think it's gonna take more than 1 minute to figure out what's wrong if this is wrong. Yes, we got another star. We are rolling. We are playing with gas and lighting fires. I guess because we're terrible people doing bad things on planes. You shouldn't light fires on planes, though. Definitely shouldn't. You know what you should do? You should follow this channel. You should follow the YouTube. You should subscribe to the YouTube link below. You should follow the Twitter. You should join the Discord so you can get notifications when we go live. Thank you so much for hanging out, having a good time. But this is everything. Everything is going to be up on the GitHub, so you can follow along at your leisure. Day 10. Pushing up right now, you see? If you have any questions, you can @ me on Twitter. You can talk to me on Discord. I'd be happy to walk through anything weird here. If you have any cool solutions of your own, I'd love to see that as well. That'd be like really dope. Maybe there's a better way than this this recursion. Although I'm actually kind of like proud of this. Like we've done some brute force cringe things recently, but this solution actually feels really clean to me. I'm really glad that we hit this on the first try. So thank you so much. I hope you have a great evening. I'm signing off for tonight because we came in here with one job only. That was our plan. Our plan was executed, and we're getting out of here because we're building up an advent calendar, and we're going to be back tomorrow. We're going to be back tomorrow with more code. Come back and do this with us again. It's going to be great. It's going to be so fun. Goodbye. Goodbye forever, or at least for today. Goodbye until tomorrow. Goodbye.